All right. So today we're going to continue talking about permutations, but I did want to. I realized I kind of forgot to mention something um, back with the counting principle. Okay. One of the it goes with what we have, with the definition that we had for counting principle, but I didn't, say this specifically. So when we have problems where we want to know, how many different combinations of something that we have, um, well, let's start with an example. One of the more common counting principle problems is they ask you to find how many different combinations of things that you can make given a certain set of things. Now it can, like this example, how many different outfits can you make from 5 shirts, 3 pairs of pants, and 4 pairs of shoes? You could do it with ice cream or pizza toppings, right? How many different combinations, how many different types of pizzas can you make with, 2 sauces and 3 cheeses and 5 toppings? And if, like I said, it follows the model that we had, but I didn't give you an example exactly like this. So I just want to go over it quickly, and actually, it's pretty straightforward. So we're not going to be spending too much time from it. So obviously, one of the ways we can do it is, we could label all our different shirts, right? Maybe I have 5 different colors, so I have a red shirt, a blue shirt, a green shirt, or I have shirt 1, shirt 2, shirt 3, shirt 4, and uh, I have 3 pairs of pants, so I have pants 1, pant 2, pant 3, and then I have shoes, shoes 1, 2, 3, 4, and I can find all the different combinations, right? I have first shirt, first pants, first shoes, 1, 2, 3, and I can count those all up. But we can use our counting principle like we did on Monday or whenever it was, and I can just multiply the different numbers. Okay, so if I have 5 different shirts and 4 different shoes and 3 different pants, it just so happens that I pick numbers that go like that, but they don't always have to be in order. I would multiply those. 5 times 4 is 20. 20 times 3 is 60. 60 different outfits. All right, so you got 2 months of outfits with only 5 shirts, 4 shoes, and 3 pants. Okay, so and that goes with anything. So if they say, I can't think of an example off the top of my head. So in biology class, a student must dissect 3 different specimens. They can select one of 9 earthworms, one of 4 pigs, and one of 7 cats. And how many ways can the student select the specimens, right? So you just multiply the numbers together. Yeah, so it's pretty straightforward, and I apologize for forgetting about it, but I just wanted to bring that up to you before we moved on. Okay, so continuing with what we did yesterday, going back to permutations, all right, we found out that the number of permutations of n elements is equal to n factorial. All right, so if I want to organize I don't know, my shirts, right? If I have 20 shirts and I want to find how many different ways I can organize them, well, the answer would be 20 factorial, which would be a very large number. Okay, as we noticed yesterday when we talked about the deck of cards and some things like that, once we get above 10 factorial, those numbers get larger and larger and larger, and it's, you know, it's a huge growth, super fast, right? But there are slightly different ways that we can address the problem, and here is one of those examples. We have eight. Oh, come on. We have 8 horses that are running in a race. In how many different ways can the horses come in first, second, and third place if there are no ties? Now, this is a slightly different. Okay, I don't care about the entire order, right? I don't care anything after third place. So this isn't just going to be 8 factorial because I'm not worried about all the horses. I just want to know how many different combinations of first, second, and third place there are. So let's set it up like we did yesterday. All right, so I'm going to have 3 blank spots. This is going to be first, this is going to be second, and this is going to be third. Well, for a first place, if we're thinking about a race, well, all 8 horses have a chance of getting first place, right? So there are 8 possibilities for first place. So theoretically, one of the horses gets first place, right? Well, now how many do we have that can come in second place? Well, if one already crossed the finish line, then for second place, we're only going to have 7 possibilities, right? And that kind of follows with what we did yesterday. For third place, well, if 2 have already crossed the finish line, well, then there are 6 horses left. But that's all I care about. So that's where I'm going to stop. Okay, I don't care about 4th, 5th, 6th, 7th, 8th. Right? So because we're only worried about first, second, and third, we are going to multiply those 3 numbers together. And I don't feel like doing it. We get we have 336 possible different outcomes. Okay, so this is a specific set of permutations. Okay, and we have it up here. It's the permutations of n elements taken r at a time. All right, and luckily we do have a quicker way to do it, or a quicker way to represent it, I should say. So let's see. Okay, so this may look familiar, but it is slightly different. The number of permutations of n elements taken r at a time, okay, is n capital P r, right? Which is similar to what we saw last week, n CR. Okay, similar setup, slightly different equation. Excuse me. This is just going to be n factorial over n minus r factorial. So here we don't have to worry about that extra r in the denominator, and it's just the 2 terms, n factorial in the numerator, n minus r factorial in the denominator. All right. So let's take a look. Going back to this example, and let's set it up. Okay, so going back to our 8 horses, let me go over this way now. All right, so we have 8 horses, and I want to know how many different ways I can find the first 3 places. So this is going to be 8p3, right? Our n is the total number of objects that we have, and the r is how many we're focusing on. Right, so I only want to know the first 3 places, first, second, and third. So that number is going to be 3. So here we're going to have 8 factorial over 8 minus 3 factorial, which is 8 factorial over 5 factorial. Now remember how we dealt with this, right? I can write everything out here. 1 times 2 times 3 times 4 times 8. And in the denominator, I'm going to have 1 times 2 times 3 times 4 times 5. And when we eliminate, look at what we're left over with. 8 times 7 times 6. Right? And that's what we had over here. 8 times 7 times 6. So this equation, this specific permutation function, okay, sets us up for how it's laid out. Right? It's a little more straightforward than the combinations, the NCR. Okay, and again, if you notice here, like I said at the beginning, okay, the order matters, right? Obviously, the order matters when you're talking about first, second, and third place. Okay, but oops, the order matters. All right, let's take a look at one more example. No, let's not do that. Okay, let's do this one. I'm going to type it out because it's going to be easier. Okay. So the one thing I do want to say is the fact that the order matters isn't always straightforward. Okay. In a sense, sometimes order matters, meaning that, you know, if one position is filled, then it can't be used for other positions. Or if one element is used, then it can't be used again. Or, you know, you need one element in a specific place. So here it's a little different setup, right? But still the order matters. So we have a pool of 12 candidates. We want to have a president, a vice president, a secretary, and a treasurer. So how many different ways can the offices be filled? Right. So once somebody becomes the president, they can't become the vice president anymore. If somebody's the secretary, they're not going to be the treasurer. All right. You can't have that. So in that sense, then the order matters. So using the function that we learned, okay, I'm just going to say first that the total number of elements that we have, our n, is going to be 12. Right? So the n is your large group of total possibilities. The r is what we want to focus it into. So here, our r is going to be 4, since we have 4 positions to fill. 1, 2, 3, 4. Oh, forgot the T for treasurer. All right, so our R is going to be 4. So we're going to have 12p4. All right, so we're going to have 12 factorial over 12 minus 4 factorial, which is going to leave us with 12 times 11 times 10 times 9. Right? And the quick way to do it is to count the numbers down from here to before the denominator, right? So I stop before I reach 8, right? And there are my 4 positions, right? 1, 2, 3, 4, president, vice president, secretary, treasurer. So I can multiply those together, 12 times 11 times 10 times 9. And with that, we have 11,880 different ways of filling those positions. So there's a lot of different possible outcomes. All right, any questions with the permutations? Okay, so I do want to backtrack then and revisit something that we used in the binomial theorem. And now we're going to use it in the context that we are now. Okay, and that is combinations. Okay, for combinations, it's similar to permutations. But the order doesn't matter. And honestly, picking between, trying to figure out when the order matters and when it does not matter is probably the trickiest part. The math in it isn't terribly complicated. All right. Once you get the hang of factorials, it's pretty straightforward. But the tricky part is distinguishing when does the order matter, when does it not matter. So let me give you an example of when the order does not matter. Again, I'm going to type it out just because writing it would be too long. I hate how it makes boxes and circles when I don't want it to. Okay. So this is similar to something that we saw, I think, on Monday, but slightly different. How many different ways can 3 letters be chosen from the letters A, B, C, D, E, and F? So before when I asked this, it was how many different arrangements can there be of A, B, C, D, E, and F? Okay, so here the order doesn't matter in how we pick it. It doesn't matter if A is first or last. All right, so in this case, okay, if I picked A, B, C, it's the same as I picked CBA. Okay, it didn't matter what order I picked it in. I picked those 3 letters. That's the same outcome. Okay, again, it doesn't matter which one's first. And any other combination that I can think of. Okay, so BCA. All it's asking me is to choose 3 letters. All right, so that's, it's a little hard to conceptualize like that. So once you get over that, then you're set with this. Okay. So here again, the order does not matter. So I can use my NCR. And I'll put that up here again for us, n minus r. So what happens is we divide by an extra term here, and that term removes all the instances where we get the same outcome. All right, so here, well, first, again, the concept of n and r is the same. N is the total number. So we have n is 6 because we have 6 letters. And now our r is 3 because we have 3. We're picking 3 letters there. So we're going to have n, I'm sorry, not n, 6c3. All right, which just happens to be 6 factorial over 3 factorial times 3 factorial. So after we simplify, I can cancel out this 3 with 1, 2, 3 from up here. So I have 4, 5, 6 over 1, 2, 3. And we can multiply, or we can, simplify here. I can get rid of this, make that a 2. I can get rid of this, make that a 2. So we have 20 different ways of choosing 3 letters from 6 letters. But if we flip the script, and if I said, the order matters, that's going to increase okay, so if the order did matter, then ABC would be different from CBA. And that would be different from BCA, right? Because A is first, B is second, C is third. Here, C is first, B is still second, but A is third. Those two are different, even though they have a common term. Okay, so the combination aspect kind of narrows it down because we don't care about the order of things. Okay. On the other hand, permutation, because things have to be specifically placed in specific areas, okay, that gives us more options and more separate outcomes. All right. So I'm going to give you some homework. The first few are just going to be straightforward, but the last couple, I'm going to ask you to think a little bit and try to figure out if we're going to need a combination or a permutation. Okay. And at first, I'm just going to ask you, what should we use, combination or permutation? And then I'll follow up with, what is it? All right. So this homework is going to be a little longer. So I will give you guys tomorrow off, so you guys can, you can try it during class tomorrow, and then we'll meet again on Friday to go over it, and we'll start with probability. I think I'm pretty much done with this stuff. Yeah. So on Friday, we'll move to probability. All right, so keep an eye out for the assignment. Again, we are not meeting tomorrow. You can stop by if you'd like for extra help or just to say hi. And otherwise, I'll see you Friday. All right, guys, have a good day.